Now we'll look at a problem that's related to sorting called selection that's also well solved by quicksort partitioning. This is a simpler problem. We're given an array of n items that are ordered, and our task is to find the kth largest. There's lots of important applications for this. So, like if we wanted to find the minimum item, that's k equals 0, or the maximum item, that's k equals n minus 1, or the median, that's k equals n over 2. And there's many kinds of applications when people processing data want to find the top k or the median or other order statistics. So that's what selection is all about. Now, here's an example where we want to use theory as a guide. What kind of efficiency might we expect in a selection algorithm? Well, first of all, it's easy to see that we can solve selection in n log n time. How would we do that? Well, we just sort the array, and then if we want to find the smallest, you look in the first position, or the largest, you look in the last position, or the median, you look in the middle. In fact, if k is small, the running time is going to be proportional to n. Because if you're looking for the smallest, you can just go through the array and find the smallest in one pass through. Or for 2, you find it in 2 passes through. So you can imagine trying to look for a selection algorithm that takes time proportional to n. And also the lower bound is n because you have to look at everything. If you don't look at everything, you might miss the one item that you're looking for. So from these observations, it's clear that what we'd like is a selection algorithm that takes linear time. But at this point, the question is there a linear time algorithm that works for every k? Or possibly selection is as hard as sorting. This kind of question plagued a lot of people in the late 60s, early 70s as these types of problems emerged for computing applications. So it's an interesting question to think about for sure. Well, in his original paper in 1961, Hoare gave a solution to the selection problem based on partitioning. And the idea is just a version of quicksort in a way. We're going to do our partitioning so that we get entry A of j in place in the array. Nobody to the left is larger, nobody to the right is bigger. But then when we're doing selection, what we'll do is just go in one subarray or the other, depending on where j is. If j is equal to k, we're done. We found the kth largest. If k is to the left of j, then we just do the left subfile. We just set high to j minus 1. And if k is to the right of j, we just do the right subfile, set low to j plus 1. And that's all this code does. You could do it with a recursive call, but this just does it by resetting the values of the parameters. Do one partition, then check whether your kth element is going to be in the left part or the right part. Reset low or high accordingly. If it's equal, then you found it and you return it and you keep going until you get to a point where you have only one element. That's a quicksort like implementation solving the selection problem. Notice again that it depends on the random shuffle at the beginning. That's going to be important for performance. All right, so there needs to be a mathematical analysis to characterize the running time of this program. And the fact is that quick select, this method takes linear time on the average. We won't give the full proof. It's actually quite a bit more complicated than the one just done for quicksort. But intuitively, we can see kind of what happens. Each partitioning step maybe splits the array approximately in half. So that means you'd have, if it did exactly in half, you'd have n plus n over 2 plus n over 4 and so forth, which adds up to about 2n compares, so linear cost. If you do it actually doesn't cut it in half exactly each time, only on average. So you need a fuller analysis like the one we did for quicksort. And the bottom line of that analysis gives the number of comparisons required as a function of n and of k in terms of this formula here. And if you plug in k equals n over 2, you get the result that the number of compares required to find the median, and that's the highest value this formula can take, is 2 plus 2 natural log of 2. So linear time to find the kth largest for any value of k. Now again, it's going to use, this is a method that's linear time on the average. It's actually going to be quadratic in the worst case. But again, the chance that that'll happen with a random shuffle is less than the chance that we'll be struck by lightning. It's a probabilistic guaranteed fast algorithm. Now, from a theoretical standpoint, that's a little unsatisfied. And in 1973, there's a famous paper that found a compare-based selection algorithm that guarantees to solve the problem in linear time. This was a real landmark in the theory of algorithms because for a long time it was not known. We knew we could have the average case be linear time, but could we find a worst case? And this paper found such a construction. Now, in practice, this construction is rather high, so the method's not really used in practice, and so there is still the goal of a fast, guaranteed linear time selection algorithm that maybe somebody in this class will invent someday. This is another example where we use theory as a guide. It's still worthwhile to look for a practical linear time worst case algorithm. Maybe somebody in this class will invent that. But until something like that is discovered, use the quick select based on quicksort partitioning, and you can get linear time selection when you don't need a full sort. That's selection, a simple problem like sorting that is well solved with quicksort partitioning.